The paper I'm going to present is titled Making AI Meaningful Again from Jobst, Landgrebe and Barry Smith. The AI field is currently experiencing a period of enthusiasm, fired above all by the success of deep neural networks. We are going to analyze the current problems underlying the current view of AI due to this success, and then an alternative approach to natural language processing proposed by the authors, where there's a role for philosophy. The current state of the art in AI is dominated by deep learning, which is a subfield of applied math where stochastic models learn a desired behavior in response to some input stimuli. These models are tuned using input-output pairs constituting a training corpus of data. Each input-output pair is an instance of the desired response in relation to some input encoded in digital form. The purpose of this training is to make the model able to generalize to new unseen input after being exposed to a sufficiently big training set, showing up the full variability of all input associated to the same output. Furthermore, this set of input-output tuples must be consistent, meaning that similar input should lead to similar output in a way that patterns can be identified versus an erratic or chaotic process. These patterns must also show up repetitively during training in order to effectively adjust prior probabilities. Consequently, the output of deep neural networks is just probabilistic, and thus uncertain. In addition, deep learning is also agnostic, in the sense that the models have no prior knowledge about the task being performed. In a recent publication by Google titled "Attention is All You Need," they propose a stochastic model called Transformer, which was trained for natural language translation from English to German and from English to French. The model was trained using 36 million sentence pair from English to German and 4.5 million from English to German. Transformer is totally agnostic, having no knowledge of linguistics, and the technique used to embed each sentence into an encoding vector of real numbers led to discarding all information about the context of the input sentences. Now a question arises: how well does this model do? Using Bleu metric, measuring on a scale from 0 to 100 the degree of matching between the machine translation and some human gold standard translation, the model scored 28.4 for English to German and 41.8 for English to French. An average bilingual human usually scores between 75 and 85 out of 100. This is the state of the art in machine translation. The solution proposed by the authors to overcome the limitations of agnostic deep neural networks, and also what they consider a way to make AI meaningful again, is a philosophy-driven natural language processing AI system applicable to specific domains, for which it must be customized to. In particular, they propose a semantics-based approach attempting to deal with natural language in a similar way to how humans assign meaning to the entities of the language itself. The method combines stochastic inference models with a logic-based machinery, trying to incorporate prior knowledge into the decision-making process. Such a model has its root in the work of Patrick Hayes, in particular to what he called naive physics, which is a theory based on a set of ontologies, each of which captures the common sense knowledge that humans attribute to specific domains in the physical world. However, the problem with this kind of strong logic-based approaches is the one of computability, imposing strong restrictions on the expressiveness of the logic formalism which can be used. An example of these limitations is visible in the web ontology language, which is a semantic web language designed to represent common sense knowledge limited to at most two entities relations. These are just some of the reasons why pure logic-based AI has never driven meaningful real-life applications. An ontology is a taxonomic hierarchy where entities are related to each other by the relation of greater and lesser. They are of two types: domain and top-level ontologies. Domain ontologies specify the relationships between the entities of a specific domain. On the other hand, top-level ontologies deal with categories shared across a broad range of domains. Before delving into the actual functioning of the proposed solution, the authors point out what are the requirements they believe any real-world AI system should satisfy. Exactness means that decisions cannot be approximative. In some way, it's a way to reduce the uncertainty in the outcome. Information security prevents that slight perturbation of the input might lead to erroneous outputs. Robustness is the ability to operate in different situations and eventually to detect the inability to take actions informing the human operator. Data parsimony stands for the magnitude of the required training dataset. Most realistic settings limit the availability of training samples to no more than a few million. Semantic fidelity is the capacity to contextualize the input sentences into an environment. Inference is the ability to make reasoning and requires dealing with time and to make a distinction between correlation and causation. Finally, prior knowledge is also required to interpret situations. To represent the complete semantics of natural language, we would need a high-order intentional logic formalism, making the computation unfeasible. Indeed, computability requires both robustness and completeness, while decidability is not strictly necessary. The absence of decidability would imply that the computation might not terminate. But this can be solved by interrupting the search after a certain period of time and leaving the decision to humans. So, in order to approximate the complex natural language semantics while allowing computability, a set of different computable logical formalisms are used together. For example, fundamental constructs of the language are represented in first-order logic, while propositional temporal logic is used to deal with timelines, and intentional sentences are managed with modal logic. However, such a system does not strive for general AI. The AI must also be able to deal with ambiguity, vagueness, and indeterminacy of the natural language. Here is an example of how the different formalisms cooperate to resolve an ambiguity in text. In this case, the transitive verb in the second sentence may or may not have an existing object. In the formal representation, we have unary predicates expressing nouns and modifiers indicating syntactical relationships. Verbs are represented through non-unary predicates. The subscript P indicates the past tense, while the subscript I indicates intentionality of the transitive verb. In this case, the intentionality indicator is given by the temporal dependence between the two sentences plus the negation in the first sentence. This indicator is used in a subsequent step to search for a possible object eventually satisfying the intentional predicate. The process of transforming text into logic is summarized by this pipeline. In the first step, the input text is transformed into a set of logical formulae, gamma, using deep neural networks to perform stochastic error correction and syntactic tagging. In the second step, gamma is transformed into a set of computable formulae, delta, using the suite of logical formalism we saw before, also with the support of ontologies. Finally, the last step requires the use of mechanical theorem proving to infer the phi's. Each phi is a logical consequence of some expressions from the set delta. It's also required each phi to be an instance of omega, which is a handcrafted ontology expressing the target semantics of the specific domain of interest that can be attributed to the input sentences. The only manual input is omega, which must be created once at design time. In conclusion, in spite of who proclaimed the death of philosophy in the 20th century, the success of philosophy-driven, context and task-specific AI systems like the one we've been discussing is a proof that philosophy will play an important role in the enforcement of applied sciences in the digital era.